Great. Thanks, Ryan. Thanks, Andre, for letting us present this paper. Let me find the right screen to share here. Okay. Ryan, can you just give me a thumbs up if you guys can see the slides?
I can.
Okay. Excellent. Okay. Great. So this is I'm going to give some caveats up front. This is very preliminary. I would think of this as the alpha version of this presentation. We're working on a first draft of a paper that'll probably be ready in another week or so. This is joint work, and I'm a little sloppy. I didn't even list my co-authors here. So this is joint work with Zack, who's at the University of Houston, and Malcolm Wardlaw, who's at the University of Georgia. Malcolm is here. I'm actually not sure that Zack is here. So Zack is traveling at the moment and wasn't sure whether he would have internet access. So he may not be with us. Okay. So this is essentially a methodological paper. It's the first methodological paper I've ever been involved in. And so let me just sort of tell you what it is we're sort of thinking about and what it is we're doing here. Okay. So one observation is that there's a growing use of what we would call count data in constructing outcome variables in corporate finance over the last decade or so. And by count data, I mean data that can only take on non-negative integer values, so 0, 1, 2, 3, et cetera. And the leading application, at least in corporate finance, for the use of this count data is in using patent data, right? Where people will regress, some measure of the number of patents on some covariates in trying to say something about how different economic forces affect innovation. So patents are sort of a stand-in for innovation in that sense, okay? Or patent citations are also used as another count variable in these types of applications. Yeah. Now, there's very little guidance in finance on how to work with count data. There's some guidance in other disciplines of economics. And what we're going to sort of do here is bring some of that together, and we'll say some things that are kind of beyond what's described in other areas as well. But basically what we're going to try to do is assess different approaches to using count-based outcome data. And then we're going to revisit some existing results from the innovation literature, where we're going to run some regressions that are going to involve patents. And we're going to see how robust those estimates are to estimating different types of models and sort of what we can say about what might drive disconnects between different types of models as well. Okay. So the way count data is used in practice in finance is the following, right? So just as a thought experiment, you might imagine starting off by just regressing, the number of patents. Let's say Y is the number of patents on some covariates, and that would be sort of the way we would normally do things. The problem, though, is that count data distribution is often highly skewed, right? So, by definition, it can't take on negative values. Oftentimes, and this is certainly true with the patent data, there are a lot of zeros. So you get this very skewed distribution, which means that an OLS regression like the one that's sort of described on the first line here is going to be inefficient. And then we always have to worry about the fact that there might be some outliers out there that are going to have a big effect on our estimates. So the sort of standard way of solving this problem would be to just do something like take the log of the count variable, right? So that's going to effectively get rid of a lot of this skewness. It's going to result in a more symmetric distribution. The problem, though, is that, as I mentioned, count data sets often have lots of zeros, right? If you look at the corporate patenting data, 30 to 40% of the observations are zeros in many cases. The problem, of course, is that the log of 0 is undefined. So the standard approach that people take to get around this problem is they will just add 1 to the count variable before they take the log, right? And so then you'd estimate a regression that's something like the following, where the dependent variable is the log of 1 plus the count variable, and then you've got a bunch of covariates on the right-hand side. And again, this is the standard approach. We're going to call this the log of 1 plus regression throughout. So just if you see log of 1 plus 1 and you're not sure what it means this regression. Okay. And so the problem is we don't really know anything about the econometric properties of this log of 1 plus regression, right? And what I'm going to show you is that there are some problems associated with this log of 1 plus regression, and I'll sort of show you some alternatives. So basically, the big takeaways here are that this log of 1 plus regression produces estimates that don't have a natural interpretation, either in terms of a conditional expectation function or in terms of an elasticity, right? Which is usually what we think of when we're thinking about log regressions. And then the other problem, which I would sort of argue is the bigger problem, is that the estimates that come from a log of 1 plus regression can be biased and inconsistent, and may in fact have the wrong sign, right? Which sort of makes inference really tricky. And there are really two potential causes of this inconsistency. One is heteroskedasticity in the count itself, right? Normally we don't think about heteroskedasticity as causing bias. I'll explain to you why in this particular setting it may cause bias. And the other is that you're adding this constant before logging, and that also is going to potentially bias the estimates that are coming out of the model. Okay, so there's sort of two solutions that we would propose here. One is to estimate Poisson models, right? So a Poisson model is a count model. It's sort of meant to take on count data. Under the standard exogeneity assumptions, the Poisson model is both unbiased and consistent. Okay, so it sort of has that desirable property. The other thing that's worth noting is that these Poisson models can admit fixed effects, right? So if you're worried about the fact that you want to absorb heterogeneity at, say, the firm level, so you'd like to have some firm fixed effects, Poisson models can account for firm fixed effects just in the same way that an OLS model can account for firm fixed effects. Okay, so what we're going to see then is when we actually go back and try to replicate some of the existing papers in the innovation literature, that Poisson estimates, which again are unbiased and consistent under the standard exogeneity assumptions, are frequently going to produce different signs and different magnitudes than the log of 1+ regressions that people typically run. Okay, so I guess let me pause for a second. Are there any questions?
So far, no questions, Jonathan.
Okay, all right, excellent. Okay, we'll keep moving then. Okay, so as I mentioned, there's sort of been this kind of growth in the use of count data over the last decade or so. So in the last 10 years, this is kind of a coarse count, so this is an approximate number, but there's something like 45 papers that have been published in the JF, the JFE, and the RFS that use a patent-based outcome variable, okay? And there are a bunch more in management science and JFQA and other journals as well. And in approximately 90% of these papers, the authors are estimating log of 1+ regressions, right? And in most cases, it's exclusively log of 1+ regression. So there aren't other forms of estimation that are attempted. Okay, there are also a whole bunch of working papers out there that are estimating these types of regressions as well. Okay, now there are other count outcome variables that are starting to be used in finance research and corporate finance research. I think this is one of the things that's becoming a more important issue. So things like workplace injuries, right? That's a count-based variable. Environmental releases, trademarks, number of movies. So our co-author Zack has a paper where he's looking at the number of movies that an actor is acting in as a left-hand side variable. Research paper citations. These things are all kind of inherently count-based variables, and so I think it's important then to understand when we're estimating these regressions, what exactly the econometric properties of the estimates we're going to get out of these regressions end up being. Okay,
Jonathan.
So yes.
Before you move on, so what about Heckman or Tobit? Are you going to be looking at any of these other models? Yes.
So we're not, and I think that, there are reasons why we don't generally use a lot of like Tobit type models, and I think the biggest reason in empirical corporate finance applications is that the Tobit model doesn't admit fixed effects. And so, in almost every empirical corporate finance paper, we want to absorb some fixed effects, whether it's firm fixed effects or industry and year fixed effects. And the Tobit model doesn't really speak to that, so it doesn't admit fixed effects. And I think that's why those models are not really used fairly broadly in practice in empirical corporate finance. So we're not really going to have anything to say about those models. And I think that's really the big limitation, is the inability to put fixed effects in those models.
So one question about Poisson models: are they flexible enough to make IV type estimations?
So that's a good question. To my knowledge, they are not. This is, again, you're going to very quickly see that the limits of my econometric knowledge are going to come into play here. I am not an econometrician by training. My sense is that Poisson models do not lend themselves to IV regression. So that may be a limitation of using a Poisson model type approach. Most of the papers in this sort of corporate innovation literature are simply estimating OLS regression. So they're not doing IV regressions. Things, I guess, would get more complicated. That's something we need to think a bit more about is, if somebody wants to estimate an IV regression, do we have sort of a natural proposed solution for how that could be done without sort of running into some of the problems with these log of 1+ regressions?
So just very quickly, sorry, I meant to chime in. The answer actually is yes.
Okay.
So they do in fact admit an IV specification, just to be clear.
Okay. And for what it's worth, Malcolm is a much better econometrician than I am, so I'm gonna ask him to jump in if I say anything that's incorrect econometrically and get me out of trouble here. Okay.
Okay. Thanks.
All right. Of course.
Oh, sorry. One more related question. What about fractional logit or other classes of these models that allow you to model the zero separately?
Yeah. So things like zero inflated Poisson models and these sorts of things. Again, the issue there is going to be the ability to incorporate fixed effects. And my understanding is that those models, they're sort of inherently nonlinear models by nature. And so we can't introduce sort of proper fixed effects into those models, right? The other sort of, I think, reasonable question, right? So those types of models are designed for cases where there are units of observation that are simply not exposed to whatever the underlying arrival rate is. So even with a Poisson distribution, right, you're going to get zeros depending on what the parameter in the Poisson distribution is. There's nothing wrong with having zeros in those cases. What we do worry a bit about is that maybe, there's some firms that could just never patent for whatever reason. So we shouldn't really be thinking about the effect of covariates on their patenting intensity. And that's what these zero inflated Poisson and zero inflated negative binomial type models are designed to handle. But again, I think the real limitation there is the inability to incorporate fixed effects into those models.
Okay, let's move on.
Okay, great. Okay, so the first thing I want to talk about is sort of the fact that these log of 1+ models don't really have natural interpretations. Okay, so again, this is sort of the regression that we're talking about here, right? The log of 1 + y on the left-hand side, and then you got some covariates on the right-hand side. Okay, and the first problem is that these things don't really have a natural interpretation in terms of a conditional expectation function, right? So if you were to sort of ask, Josh Angrist kind of how we should be thinking about the outcomes that we're getting from these regressions, he would say, yeah, what we really care about is the conditional expectation function. And that's not something that we can really say something easily about using these types of regressions, right? So, what we're generally interested in terms of a conditional expectation function is the mean of y as a function of x, not really the mean of the log of 1 + y as a function of x, right? That in and of itself doesn't necessarily have a lot of meaning. Under the assumption, under sort of the standard exogeneity assumption, right? So the epsilons are not correlated with the x's. Then if we're using this log of 1 + y model, right, you can just exponentiate both sides and subtract 1 and take an expectation. And what you'll get is that the expected value of y with respect to x that's implied by the model is something like the expected value of the exponential of alpha plus beta x plus epsilon collectively minus 1. And since the epsilon is in the exponential function, right, it's effectively a multiplicative error term. And so you can sort of break this out and write this as the expected value of alpha plus beta x times the expected value of e to the epsilon, right, and then minus 1. And so when you compute a marginal effect, you're going to be stuck with this expected value of e to the epsilon, right? And so if you want to interpret this marginal effect in terms of something meaningful, you have to have some way of dealing with the fact that you've got this expected value that's a function of the error term that's in that marginal effect. So you need to either estimate the expected value of e to the epsilon from the data, or make some distributional assumption that would allow you to compute what e to the epsilon should be, or the expected value of e to the epsilon should be, if you want to do interpretation here. Right. The same problem exists, by the way, even if you're not adding a constant, even if it's just the log of y as the left-hand side variable. So this is always an issue with interpreting log regressions. Now, the way we generally interpret log regressions is in terms of semi-elasticities. Okay, so the problem is that once you add the constant to y and you take a log, you no longer have a natural interpretation in terms of a semi-elasticity either. Okay, so you sort of lose the one thing that's sort of useful about log of y type regressions, right? So if we start off with a log of y regression, where log of y is on the left-hand side, that beta is going to end up capturing the semi-elasticity, right? So the change in the expected value of y with x, divided by the expected value of y. Okay. The problem is that once we're adding a 1 to y before we take the log, what we end up with is the change in the expected value of y with respect to x divided by 1 plus the expected value of y, right? And so again, we have an interpretation in terms of a semi-elasticity of 1 plus y with respect to x. But that's not generally something that we're going to be interested in if we're trying to sort of make statements about the quantitative implications of a particular set of estimates. Okay, so we sort of lose that semi-elasticity. Of course, this constant 1 is arbitrary, right? You could put in a different constant. You could put in 0.01 or you could put in 10, and that's going to change the semi-elasticity, but not in ways that are necessarily going to make them any more or less meaningful, right? So anytime we're adding a constant, we're going to lose that nice sort of natural semi-elasticity interpretation. Okay, so let me pause here for a second. Are there any questions?
There is it seems like it might be a point about the Poisson regressions. It says the Poisson regression requires the equivariance assumption.
Yeah.
In that the mean equals the variance. So this works well if the dependent variable is small.
Yep. So I'm actually going to talk about that in just a second. When we talk about Poisson regressions, the answer to that question is that is a restriction that the Poisson model imposes, but the Poisson estimates are still unbiased and consistent even if that condition is violated. So that it has an implication for efficiency, but not for consistency. And I'll talk a bit more about that in just a bit.
Okay, there's a question. What about Cox transformations?
I don't know that we've got, Malcolm, you can jump in if you want to. I don't know that we've got anything to say about Cox transformations here.
Yeah, again, I don't want to hold up the presentation. I can address that maybe later. Basically, it's Cox is a transformation to sort of try and make the errors become more normal. That sort of works in this very, very narrow case, which these count regressions almost never satisfy.
Okay. All right. So are there other questions, Ryan, or is that it?
There is a link that somebody shared. I haven't looked at it, but it seems to be a related paper. You can look.
Okay.
We'll send you the transcript.
Okay. All right. Thanks. Okay. And as I mentioned, there are related papers in non-finance literatures. I'm actually going to mention some of those papers as we go. So a lot of what we're saying is not new in the sense that other papers have pointed this out in other disciplines. A little bit of what we're saying, though, is going to be new here. And I'll sort of try to articulate what that is. Right? Now, if we sort of think about most finance applications, we may not actually care that much about the precise estimates. I think for the most part, when people look at estimates, the sort of first thing that we look at is the sign. Does the sign sort of agree with what the theory would suggest that it should agree with? And maybe we kind of care broadly about the order of magnitude. And, I think the reason for that is that if we think about most of the left-hand side variables that we're using in finance, they're not really the things that we actually care about. They're proxies for the things that we care about, right? So we don't necessarily care about patents per se. We're trying to say something about innovation, and patents are just a proxy for innovation. So, if you take an application from something like the labor economics literature, right, they care a lot about the precise magnitude of the change in the unemployment rate with respect to a change in the minimum wage, right? Because that's going to directly feed into policy decisions. In finance, we don't really care that much about the precise magnitudes because, again, we're interested in saying something about innovation, not about patents per se. And there's no kind of direct mapping from the effect of a covariate on the number of patents into the effect of the covariate on sort of the true measure of innovation. So I think we're sort of more interested in order of magnitude and really in many cases in signs than we are in those precise estimates. The problem is that these log of 1+ estimates may also give the wrong sign or the wrong order of magnitude. Okay, and so there are going to be issues in terms of bias and consistency when it comes to these log of 1+ regressions. Okay, so there are really going to be two reasons for this. So the first is heteroskedasticity, right, which you normally don't think of as being something that induces bias. Okay, so think about the following, right? So if we're estimating this regression, right, so the log of 1 + y on covariates, then again we can just exponentiate. So we can write 1 + y is equal to the exponential of alpha plus beta x plus epsilon. And that means that this sort of error term is effectively multiplicative, right? So this eta is equal to e to the epsilon, and we'll generally assume that eta is equal to 1, so that the expected value of whatever the thing is on the left-hand side is equal to the exponential of alpha plus beta x, right? That's the kind of interpretation we would like to be able to get to. Okay? So the identifying assumption here is that the etas, that these sort of multiplicative error terms, are uncorrelated with the x's. Okay? The problem is that if the variance of eta as a function of x is correlated with the x's, right? If we have heteroskedasticity in the y's themselves, then this error term may effectively become correlated with the x's. Okay, and this causes both bias and inconsistency in the estimates that we're taking out of this these log of 1+ regressions. Okay, and I'm going to show you a couple of pictures on the next few slides. I think will make it a little bit more clear why it is that heteroskedasticity, in combination with this nonlinear transformation, potentially ends up inducing bias in the estimates. Okay, and so even if x doesn't actually affect y, we may incorrectly conclude that it does affect y if it affects the variance of y. Okay, and again, when we're sort of thinking about how we might solve this problem, then the natural way we'd sort of deal with heteroskedasticity is to think about something like White's correction. But the problem here is not with the standard error, right? Which is what the White correction fixes. It's with the coefficient itself. And so White's correction is not going to help us here. Okay, and so we can also say something about how the the relationship of the variance of the error terms as a function of eta, the sign of that relationship, what the implications that are for the direction of the bias, the inconsistency that we're going to see. Okay? And again, this is not specific to these log of 1+ regressions. If you're estimating any log transform regression, these same issues are going to exist. And there's a paper by Silva and Tinreo. It's called The Log of Gravity. It's a fairly well-known paper in the trade literature that sort of talks a lot about this. And a lot of what we're saying really is kind of built on what they're saying in their paper. Okay? So let me just sort of show you a couple of slides, a couple of pictures to make it clear why this heteroskedasticity causes problems. And I'll stop and take questions at that stage. Okay. So to start off, we think about a very simple example. So again, we're going to assume that y is given by this sort of standard function, and let's assume that we're operating under the null hypothesis. So the beta here is 0, right? Which means that basically y is just equal to this error term. Okay? And let's assume the error term can take on two values. It can take on 1 minus x, and it can take on the value of 1 plus x. So we're going to induce heteroskedasticity in the error term by making it a function of x. Let's assume these are equally likely, so the mean of that error is going to be 1, which is the desirable property. Okay, and the expected value of the error term is not going to change as the x is changing, but the variance is going to change. Okay, so these sort of green dots basically plot out what the value of y is going to be depending on whether the error term is 1 minus x or 1 plus x. So this sort of upward sloping set of dots here. This is going to be the case where the error is 1 plus x, the downward sloping set of dots. This is going to be the case where the error is 1 minus x. Again, if we just take a mean, so basically, if you just pick a particular x value, we have, two possible outcomes, right, which are sort of represented by the lower and the upper green dots. And the mean is going to be simply the midpoint of those two. And again, by construction, that mean is going to be the same for every value of x, right? And that's just going to give us this simple conditional expectation that's basically represented by this flat line, right? Which makes sense because we're operating under the null hypothesis where the beta is actually 0. Okay? Now let's think about what happens then if we take a log transformation of the y's, right? So not of the expected value of y, but of the y's themselves. Okay? Well, it's a nonlinear transformation and it's a concave transformation, which means that if we're sort of thinking about what the implications of that transformation are going to be, they're going to have a bigger impact on the lower values of y than they are on the higher values of y. So if we're operating for very low values of x where the upper and lower values of y are both very close to the expected value, this isn't really going to have much of an effect. But it's going to be a problem when we're getting out here where we have the variance being significantly larger with higher values of x. So the problem now is that we have either very high or very low values of y. And when we do this nonlinear transformation, you can see that we're really going to the fact that you're going to have the nonlinear transformation is going to have a bigger impact on the lower values and the higher values because of its concavity, is going to start dragging down that expected value of the log of 1 plus y as a function of x as we get further and further out to the right. Okay, and so what this is going to do is it's going to introduce negative bias, right? You're going to end up, if you were to estimate a log of 1 plus regression here, you would estimate a negative coefficient, even though the expected value of y with respect to x is not changing with x, right? That we're operating under the null hypothesis. Okay, and if you want to see the math, I kind of put the math here in the very sort of right-hand side of the slide, just so that you can sort of see exactly how that works. Okay, the opposite problem is going to be true if we have a situation where the variance is higher for lower values of x, right? There, it's exactly the same intuition, right? The problem is that we're going to end up, when you do this nonlinear transformation, this log transformation, you end up with a bigger impact on these lower values of x, where there's a bigger spread in the possible y's. And what that's going to do is it's going to cause an upward bias in the estimates that you would get out of a log 1 plus regression. Okay, so those are sort of the two scenarios that you can end up with. They're sort of simple cases where we have a monotonic relationship between the variance of y with respect to x and the x variables. Okay, all right. Let me pause for a second and see if there are any questions.
There are no questions, but the paper that you referred to, Log of Gravity, is actually the same paper Mike
okay, excellent.
linked to in the comments. Yeah.
That's right. Yeah, and this is the insight here is going to be exactly the same if this is the log of y instead of the log of 1 plus y. So the 1 plus here isn't the important factor. It's the fact that it's a nonlinear transformation of a of a variable that may have heteroskedasticity in it that's causing the problem. Okay. All right. So then the other issue that we have is the addition of the constant. And the addition of the constant is going to potentially end up inducing bias as well, right? So presumably when we're estimating something like a log of 1 plus regression, we're trying to get something like a conditional expectation where we kind of have in mind that's equal to some exponential, right? And this is what you would get out of the Poisson model, right? So if we sort of think about what the marginal effects would be in this case, right? It's just beta times times this exponential function, assuming that the errors are homoskedastic, right? As we've already seen, if the errors are heteroskedastic, we're going to run into a problem with any sort of type of nonlinear regression. Okay, so in this case, if we were to estimate a log of 1 plus regression, the problem is that what we're going to end up with here, when we think about what how the log of 1 plus y is changing with respect to x, is that we're going to end up with this 1 plus y term that's going to be in the denominator, right? So it's exactly the same as what we would get if we were estimating something like Poisson regression, but now we're dividing by 1 plus y. Okay, and what that means is that because we're adding this constant, we're no longer going to get an estimate of the thing that we're presumably trying to actually estimate here, right? And the problem sort of boils down to the fact that the sum of logs and the log of sums is not the same thing, right? This is a Jensen's inequality problem in that sense. And the problem would exist even if we're adding constants other than 1 to y before we take a log, right? You get a more general form where you have this constant sitting down here in the denominator. And in a sense, the bias is going to depend on what that constant is in a somewhat arbitrary way, right? You can choose any constant you want, and you're going to get a different marginal effect. And that marginal effect is going to have a different bias with respect to what it is that you're presumably trying to estimate, depending on the constants that you choose. Okay. All right. So let me, it's a good point to take a pause again. Any questions?
No questions at this point.
Okay. Okay. So we're moving through this pretty quickly. Okay. All right. So let me sort of talk about what at least one of our 2 proposed solutions here is going to be, which is to estimate Poisson regressions. Okay. So, with the Poisson model, the log of the expected value of the conditional expectation function is equal to alpha plus beta x. And so this gives us a nice sort of simple interpretation. And again, the big difference between the Poisson regression and a log OLS regression is that with the log OLS regression, what we get is the expected value of the log is equal to alpha plus beta x instead of the log of the expected value, right? So we're going to run into this Jensen's inequality problem, the fact that the expected value of the log and the log of the expected value are not the same thing if we're running a log regression. Okay, so this has already come up as a question, right? So the restriction that the Poisson model imposes on the data is an equality of the conditional mean and the conditional variance. And we know that in practice that restriction is likely not to actually hold, okay? So again, it's not an assumption, it's a restriction. It's actually imposed in the data. And so what happens is if that condition is actually violated in practice, as again, it often will be, the Poisson regression loses efficiency, okay? But one thing that I really want to emphasize here is that as long as the standard exogeneity conditions hold, as long as the errors are not correlated with the x's, then even if the conditional mean and conditional variance equivalence condition doesn't hold, Poisson estimates are still unbiased and inconsistent. Okay, and this is one of the things where you don't have to take my word for it. Look in Wooldridge, and he actually talks about this: the fact that you get unbiased and inconsistent estimates from the Poisson regression, even if the equality of the conditional mean and variance condition doesn't hold. Okay. So the other thing that's worth noting here is that, again, a lot of times in applications in empirical corporate finance, we want to be able to control for things like firm fixed effects. Okay. Well, Poisson models can accommodate firm fixed effects, right? The sort of the interpretation of the firm fixed effect is a little bit different because with a Poisson estimate, what we're ultimately going to end up with is an interpretation that's kind of a multiplicative function of some baseline. But that baseline can be different for every unit of observation, for every firm in the case of a firm fixed effects type regression. Okay, and this used to actually be, it was one of the things where you could do this, but in practice you would run into some computational issues. And Malcolm and I certainly ran into this. So on the workplace, the first workplace injury paper that we wrote, we were trying to estimate Poisson regressions with a whole bunch of fixed effects. And you kind of run your command in Stata, and then you sit and you wait for 15 or 20 minutes while Stata tries to converge. Now there's a module called PPML HDFE. It was created by Sergio Correa, who's with the Fed, and it allows for very quick estimation of high dimensional fixed effects Poisson models using a maximum likelihood estimation type approach. So now instead of waiting 15 minutes for your estimates, you might wait 15 seconds for your estimates. So the practical problem with trying to estimate Poisson models with high dimensional fixed effects, I think, no longer exists, and that was really maybe one of the sort of valid reasons why you might not want to spend a lot of time trying to estimate these types of models. Okay. All right. So let me stop and see if there are any questions about Poisson estimation.
Nope. You appear to be
okay.
Everybody's on the same page.
Yeah, everybody's on the same page. Either everybody's with me or everybody's completely lost. This is what I say in class when people aren't asking a lot of questions. Again, a lot of this is sort of a rehash of econometrics 101. But I think a lot of us forget, we sort of know that there's this this conditional mean and variance equivalence restriction that the Poisson model imposes. I think what a lot of us sort of forget about, and I certainly had sort of forgotten about this until we started working on this project, is that it doesn't have any implications for the efficiency, sorry, for the consistency of the estimates, only for the efficiency of the estimates, okay? Which is a problem, of course, but I would sort of argue that that's maybe the lesser of the two evils. I'd rather have consistent estimates that are perhaps somewhat imprecise than very precise but inconsistent estimates. Okay, so again, this Poisson model is interpretable in terms of a conditional expectation function. So the conditional expectation function is a little bit hard to interpret, right? You can't just look at the coefficient. The conditional expectation is actually going to vary depending on the x's, and people will do things like say, well, we'll take the mean of the distribution of the x variables and interpret the conditional expectation function in those terms. It's also interpretable in terms of an incidence rate ratio, okay, which is a sort of multiplicative interpretation I was talking about, which is kind of like an elasticity in a sense, okay? Now, the other model that we might think about estimating if we're dealing with count data is the negative binomial model, okay? And the negative binomial model doesn't impose this restriction that the conditional mean and conditional variance have to be the same. So it's more flexible in that sense, which is a desirable property. And generally, it's going to be more efficient than the Poisson model if that condition doesn't hold. The problem with the negative binomial model, again, kind of coming back to practical issues, is that the negative binomial model doesn't admit fixed effects. Okay, and so if you want to control for unobserved firm heterogeneity, kind of time invariant firm heterogeneity, you're not going to be able to use a negative binomial model to do that. And so that's why we're making an argument that the Poisson model is actually probably the right model to be estimating here. Okay. All right. So I keep seeing things pop up in the chat, but I'm ignoring the chat. Are there any other questions?
People are excited about that Stata module.
Okay, cool. So yeah, if you haven't checked it out before, again, it's really cool, right? It runs really quickly, and it's definitely an upgrade over the sort of the original Poisson regression.
There is a question though. How can we use the Poisson regression when y has a linear relationship with x?
Yeah. So if y has a linear relationship with x, then presumably what you want to be, you want to be estimating just an OLS model at that point, right? So generally speaking, if we think about count data arrival processes, it's kind of hard to sort of think about y having a linear relationship with x, right? That presumably means that y can take on negative values, right? And count variables by definition can't take on negative values. So I would think if we're thinking about anything like if you wrote down any sort of arrival process, you're going to get something that's exponential. That's not going to be a linear function of the x's. It's going to be an exponential function that itself is linear in the x's, but because it's an exponential function, it's going to be nonlinear in the x's. So it's hard to think about linear relationships that would make sense in the context of count data. Okay, but if you have a linear relationship, just estimate an OLS model, right? And you shouldn't have any problems in that case.
Thanks.
Okay, thank you. Okay, so then what we're going to do is we're going to replicate some of these patent papers. I'm going to show you replications from 5 of these. We picked these 5 because they were the easiest to replicate with kind of off-the-shelf data for no other reason than that. So there's nothing sort of specific about these papers other than the ease of replication that allowed us to choose them. And I'll show you both the original estimation in the paper as well as our efforts to replicate. The good news is we were actually able to effectively replicate all 5 of these papers. Which, if you've done replications before, if you said you're going to get 5 out of 5, I would say, yeah, that's that might happen like 1 out of every 10 times. So we were happy that we were able to actually replicate the estimates from all of these papers. So the first paper is this paper by Hirschleifer, Lowe, and Teo, which was published back in 2012. Basically, they were trying to say something about the effects of CEO overconfidence on innovation. All of these papers, by the way, are using patents to construct left-hand side variables. Okay, so from the paper itself, the point estimate is 0.093. It's significant at the 5% level. I'm just going to choose one specification, which is going to be sort of the most kind of parsimonious specification in the paper. We've tried some of the other specifications, and you sort of get similar conclusions. So we were able to very closely replicate that 0.093. So in our replication, we came up with 0.110. And when we estimate Poisson models, we actually get something that's slightly larger in terms of the estimate, also significant at the 10% level. So I would sort of suggest that in this paper, the Poisson estimate and the log of 1+ estimate are pretty much giving us the same answer. Okay, so in this paper, there doesn't seem to be much of a discrepancy. Okay, the second paper is this Tien paper. So this paper is trying to say something about the effect of analyst coverage on innovation. So the explanatory variable here is the log of coverage. This is the estimate from the paper. So the point estimate is minus 0.053, highly significant at the 1% level. Again, we get a slightly different point estimate, which doesn't really mean very much. Our sample is going to end up being slightly different here, but it has the same sign, has the same level of significance. It's about half the value. But in this case, once we estimate the Poisson model, we get a point estimate that actually has the opposite sign, okay, and about the same magnitude. It's much less precisely estimated, so the standard errors are quite a bit bigger. And again, that may be a function of the fact that we have violations of this conditional mean and conditional variance equivalence restriction that may cause these point estimates to be less precise. But it's a little bit worrying that the sign actually flips when we estimate a Poisson regression, which again should be unbiased and consistent under the standard exogeneity assumptions, while the log of 1+ regression is not going to be unbiased and inconsistent in the presence of heteroskedasticity. And I'll come back and talk a bit more about that here a little bit later as well. And then we also have to worry about the fact that we're adding a 1 to this before we're estimating, and that can also cause us to have bias and inconsistency. Okay. The next paper is a paper that's looking at the effect of illiquidity in the stock market on innovation. Here we get a positive relationship. So again, this is from the paper. The point estimate is 0.141, significant at the 1% level. Here we get a very close estimate to the paper. Partly that's because the authors of this paper were nice enough to share their data with us. So we have a slightly different sample for reasons that I'm not entirely sure of. But the point estimate is almost exactly the same. But then when we estimate a Poisson model, we get something that's actually negative and insignificant in this case. So again, we're getting a pretty big discrepancy between what the log of 1+ model tells us and what the Poisson model tells us. And again, that would worry me a little bit, given the fact that we know that there may be some bias in this log of 1+ model. Okay, a couple of other papers. So this is a paper that's looking at the effect of interstate bank deregulation on innovation. This is a paper that actually does estimate a Poisson model. Okay, so it's one of the very few that we found in the finance literature that's using patents and actually estimating a Poisson model. So the coefficient here is positive. It's 0.119, significant at the 1% level. Again, we were able to sort of get a really close estimate in terms of our replication. So our estimate ends up being 0.1, which is pretty much spot on. Also significant at the 5% level. When we estimate a log of 1+ model, right? So in this paper, we're not starting with the log of 1+ model and estimating a Poisson model. We're starting with a Poisson model and estimating a log of 1+ model. And here, when we estimate the log of 1+ model, we get a much smaller point estimate, and that point estimate is statistically insignificant. Okay? And one more paper, and then I'll stop and see if anybody has any questions. So this is a paper that's looking at the effect of a number of sort of labor-related finance policies on innovation. And this paper actually uses the log of y instead of the log of 1+ y as the dependent variable. Okay, which means they're basically throwing out all the cases where there's 0 patents, right? Because you can't take the log of 0. Again, we were able to replicate this paper pretty closely. So we get a point estimate that's certainly in the same neighborhood. When we estimate log of 1+ y instead of log of y, we still get something that's positive and significant, so it doesn't change that much. And our Poisson estimates are also positive, and they're kind of in the same neighborhood as well. Okay, so in this paper, again, the estimates you would get from a log model and the estimates you get from a Poisson model seem like they're kind of in the same ballpark, which I would sort of take as being maybe comforting that you would place at least some weight on these log regression estimates. Okay. All right, Ryan. Any more questions?
Yeah. So if you go back to the Analyst paper, the number of observations changes between the second and third specifications.
Good. Yeah.
Why?
Yeah. So the answer is that Poisson regressions, so we have fixed effects in here. If you have a 0 for the value of y for every firm in a particular, for every observation in a cell. So let's say we're talking about firm fixed effects. That means that if a firm in the data never has a patent, right, it has 0 patents in every year, the Poisson estimation will kick that entire firm out of the estimation. And the problem is that, again, the Poisson regression is going to estimate a baseline for each unit of observation. And that baseline is going to be based on the fixed effect, based on the sort of the mean over the entire sample for that firm. And the problem is if you never have a patent, that means the mean is going to be 0, and you can't divide by 0. So Poisson just kicks out all of those observations. And what that means is that if you actually look at the data, you have a whole bunch of firms that never actually patent. So what we've done, so I'm not showing it here, but we were a little bit worried that maybe somehow changing the composition of the sample is also causing these estimates to be very different. So what we did is we went back and we re-estimated the log of 1+ regression, where we're only using the observations that are being used in the Poisson regression. And that means, again, we're kicking out every firm that never has any patents at all. It doesn't mean we're kicking out all the zeros, right? Because as long as the firm had patents in some years, if it has zeros in other years, those are still going to be included in the regression. But when we do that, we get estimates that are fairly similar. They don't change that much. So it doesn't seem to be a function of the fact that we're sort of kicking out all these observations where the firm literally never patents in terms of what's driving this discrepancy.
Should there be some consistency across these regressions in the bias? Like, in other words, can you predict the bias?
Yeah, we're going to have something to say about that here in just a bit. The answer is what we're going to do, and I'll show you this in a second. We're going to do sort of a disaggregation of the bias. Well, let me put it differently. We're going to look at the disaggregation in the discrepancy between these estimates into 2 different components. One is going to be the sort of the force of heteroskedasticity in the y variables, which is something you can actually kind of estimate in the data. And the other is going to be the effect of the addition of the constant, right? And really, those are the only two things that can drive those discrepancies. And so we'll be able to say something loosely about how much bias you can attribute to one force versus the other force across these different models. Okay, but the answer is that if you don't have a heteroskedasticity issue, and adding the constant is only having a minimal effect on the estimates, you might get estimates that are in fact fairly similar. Okay, but there's certainly going to be cases where that's not going to be true, and we'll talk a bit more about that here in just a bit. Okay.
Is there a goodness of fit statistic in the Poisson regressions?
Yeah. So what you would use is you would use something like the log likelihood ratio. I'm not showing that because that's useful for comparing across different specifications within a Poisson regression, but by itself it doesn't really mean very much. So I didn't show that here, but it doesn't really tell you very much.
Okay, thanks.
All right, thanks, Ryan. Okay. Cool. Okay, so just to kind of summarize what maybe the takeaways from these replications are. So we've looked at 4 different papers. We looked at 5 altogether, but 4 different papers that were either estimating log of 1+ models or Poisson models. And in one of those 4, the estimates from the 2 models were similar. In 2 of the 4 papers, the signs were different. In one of the papers, the signs were the same, but the log of 1+ estimate was about a fourth as large as the Poisson estimate. So the order of magnitude is quite different in that paper. And the log 1+ estimate is statistically insignificant, while the Poisson estimate is significant at the 5% level. Okay. So again, it's a very small sample, right? I'm basically telling you about 4 or 5 papers here, but at least across those 4 or 5 papers, there do seem to be some pretty large discrepancies between the estimates from the log of 1+ model and the log of the Poisson model, which again, we would argue means that you should probably worry about estimating log of 1+ models when you're handling something like patent data that's going to sort of feed into your dependent variable. Okay. So now I do want to talk about these discrepancies between the estimates that you get out of a Poisson model and a log of 1 plus model. And then we're actually going to go back to the papers, the replications, and we're going to develop a tool here that we can use to try to disaggregate the discrepancies into two different components. Okay. So let me sort of talk through this slowly. This is something that we've just kind of worked this sort of logic out in the last couple of days. So we're still kind of thinking through this in some sense. So suppose that we estimate a Poisson regression and we compute the fitted values of that regression, right? So I'm going to call those y hat, right? That's just the fitted value from a Poisson regression. Okay. If we look at the coefficients from the actual Poisson regression itself, those coefficients are going to be the same as the coefficient from a Poisson regression where we're using this fitted value, right? Because all we're doing is we're taking out the noise. So the estimates themselves should be the same, okay? And it turns out that if you were to estimate an OLS regression where the dependent variable was the log of the fitted value from the Poisson regression, so the y hat, not the y, but the y hat, that's also going to have the same coefficient, okay? Because it has exactly the same exponential form, the same functional form, as long as there's no noise, right? And because we're using the predicted values by construction, there's no noise in the y values, okay? So those three things should all be the same, right? All right, now suppose that we add a constant to this y hat before we take the log, right? So we add 1, right, which is the way people normally do it, but this could be any constant, okay? The problem is that now the coefficient that we're going to get from this regression is no longer going to be the same as the coefficient that we would get from this log of y hat regression, this OLS log of y hat regression, okay? So the fact that we're adding a constant is going to change this estimate, right? And that's going to be one of the two factors that can drive this discrepancy between the Poisson estimates and the log of 1 plus estimates, okay? And now suppose that we also, in addition to adding this constant, we use the actual y variables instead of the fitted values from the Poisson regressions, okay? Well, now if we have heteroskedasticity, then the estimates we're going to get from the log regression where we're using 1 plus the fitted values of y are going to be different than the estimates we're going to get from the OLS regression where we're using the log of 1 plus the actual y's, right? And that's the heteroskedasticity problem that I talked about before. Okay, and so you can see that sort of by breaking this into these pieces, we can think about constructing a test where we try to see how much of a change we get as we go from sort of, here to here, right? From something that's going to capture the estimates from the Poisson regression to what we would get if we were to use the log of 1 plus the fitted values from the Poisson regressions. And then we can see how much of the discrepancy is being caused by using the actual values of y, where the heteroskedasticity problem is going to come in, as opposed to the fitted values of y, which by construction have no noise, and therefore there is no heteroskedasticity problem. Okay, so that's basically the test that we're going to construct here, right? So we're going to just sort of do this disaggregation. We're going to estimate the Poisson model. We're going to fit the Poisson model to get these y hat values. We're then going to estimate the log of 1 plus model using the log of 1 plus the fitted values instead of the actual values of y. And we're going to attribute the difference between the Poisson model and the log of 1 plus regressions using the fitted values to the effect of adding the constant, right? Because if we weren't adding the constant, those two things should be the same, okay? And then we're going to attribute any remaining difference to the effect of heteroskedasticity. In other words, as we look at the difference between the regression using the log of 1 plus the fitted value and the OLS regression using the log of 1 plus the actual values of y, the difference between those two we're going to attribute to heteroskedasticity. And again, those are the only two things that should be causing a discrepancy as far as we can tell between the two sets of estimates. Okay, so I'll show you the numbers here, but let me stop and see if there are any questions before we get to the picture, to the tables.
Not about this. I think there's a question we can hold.
Okay, sounds good. We'll come back to that at the end, I guess. Okay, so again, this is the estimates from the Poisson regression. So this is going to be the analyst coverage paper. Okay, so this is what I showed you in the previous slide. And this is going to be our estimates over on here on the right-hand side of the log of 1 plus, model. If we estimate the OLS model using the log of 1 plus the fitted value instead of the actual values of y, we get something, it's sort of negative, and it's about of the same order of magnitude as the actual log of 1 plus estimates. And what that would suggest to us is that heteroskedasticity here doesn't seem to be the big problem, right? That if we want to understand the discrepancy between the Poisson estimates and the log of 1 plus estimates, they seem to be driven by the addition of the constant and not by heteroskedasticity. Okay, so here's an example of a case where it looks like the addition of the constant is what's really driving most of this discrepancy between the two. Okay, this is the same sort of set of regressions in the illiquidity paper. Okay, so again, this is the Poisson regression from our replication of the illiquidity paper. This is the log of 1+ regression. And so what you can see is that when we estimate the sort of regression using the log of 1+ the fitted value, it's very different than the estimate that we get from using the log of 1+ the actual value. And that would suggest to us that heteroskedasticity is a problem when it comes to estimating this, this specific regression. Okay, that seems to actually explain more than half of the difference between the Poisson estimates and the log of 1+ estimates, right? So the Poisson estimates are still fairly different from the log of 1+ the log of 1+ y hat estimates, where we're purging out the effects of heteroskedasticity because we're using the fitted value, and the remainder of this is presumably being driven by the fact that we're adding a constant, but a lot of this seems to be driven by heteroskedasticity here. Okay? And then the third paper we're going to look at is going to be, so I'm only going to show you this for the 3 papers where there were big differences. So the third paper is going to be the interstate deregulation paper. Again, the Poisson estimate was 0.1. The OLS of log of 1+ y estimate was 0.025. They're both positive, but they're pretty different in terms of magnitude. When we estimate this log of 1+ y hat regression, again, where we're removing the effects of heteroskedasticity by using the fitted values, we get very different estimates than what we get from the Poisson regression. Okay, so it seems like a lot of the discrepancy here, again, is being driven by heteroskedasticity. Maybe a little bit's being driven by the fact that we're adding this constant. Sorry, so I'm saying that backwards. Sorry, this is the comparison to determine heteroskedasticity. So maybe a third of the difference is being driven by heteroskedasticity, and about 2/3 of the difference is being driven by the addition of the constant here. So I said that backwards to begin with. My apologies for that. Notice that there are no standard errors on these estimates. In theory, if you estimate these things, Stata will spit out a standard error. Standard error doesn't mean anything because, again, we're using the fitted value here. So there's no noise in the regression by definition. So there is no sense in which you can think about a standard error on these regressions. Okay. All right. Let me pause for a second again and see if there are any questions here.
No, there's a question about more generally about what you're doing. I think we will hold that.
Okay. Okay. Good. I only have a couple of slides left, so we can general questions we can get to here in just a second. Okay. So again, the takeaway I think from this is that if you want to know why there's a discrepancy between the Poisson regressions and the log of 1+ regressions, if you want to know what's causing the bias, both heteroskedasticity in the y variable and the fact that we're adding this constant variable seem to have some explanatory power over that bias, but the amount of the bias that each of these two factors can explain seems to vary from application to application. Okay, which in a way is kind of worrying, right? Because if it were just one, you could say, well, let's figure out a way of just solving this one problem, and then maybe we can kind of move on with our lives. The fact that there are two potential problems that we both have to solve seems like it's a bigger issue in a sense. Okay, so the alternative to estimating Poisson regressions is to estimate what we would call rate regressions. Okay, and this is sort of our alternative if we want to be normative here and sort of suggest what do we think people should be doing when they're estimating models with count data. Our argument would be either estimate a Poisson model, or if you have a good exposure variable, and I'll explain what I mean by an exposure variable in a second, you could estimate a rate regression where the outcome variable, instead of being just the raw count, is going to be the count divided by the exposure variable. Okay, and so an exposure variable is a variable that sort of captures in a very clear way the baseline exposure that every observation has to whatever the underlying arrival process is that's presumably being modeled here. Okay, so just to give you an example, since again Malcolm and I wrote this paper on workplace injuries, a lot of our regressions are based on the number of workplace injuries divided by either the number of workers or the number of hours that workers worked. And those, either the number of workers or the number of hours, seem like they're good exposure variables in the sense that you can only be injured if you're actually working, right? So the number of workers is really going to tell us about the potential number of injuries, the potential exposure to injuries, if we're talking about something like workplace injuries, okay? And so in that case, you can just estimate a regression, an OLS regression, where the dependent variable is going to be this rate variable, right? So we would estimate the workplace injuries per worker. We would estimate a regression of that on whatever explanatory variables we wanted to include on the right-hand side of the regression. And that should give us, again, unbiased and consistent estimators under the standard exogeneity conditions. Okay, and so this sort of very closely connects the expected value of y per unit of exposure. So the interpretation is maybe a little bit different in that sense to the x variable, right? Which is a little bit different than what you get out of the Poisson regression, which is more like an elasticity style interpretation. Okay, when we're talking about something like a rate regression, you really are going to get a very simple interpretation in terms of the conditional expectation function, where the conditional expectation function is the conditional expectation of the rate of injuries as opposed to just the raw number of injuries, which is probably what we really care about at the end of the day anyway, right? You know, I don't really care about whether the raw number of injuries changes as we're changing x variables. You know, what I really care about is whether the rate at which injuries are occurring kind of on a per employee basis is changing. Okay. Now, when we go back to sort of thinking about practical issues with things like patents, so again, patents are still kind of the leading application when it comes to the application of count data. The problem with patents is there's no obvious exposure variable, right? You could think about using something like research and development as your exposure variable. There's sort of two issues with that. Number one is that it's not, you know, there's the connection between the arrival rate of patents and R&D is not extremely precise. And so in that sense, you know, you're scaling by something that's kind of a noisy measure of the exposure at best. And you're still going to run into potential outlier problems where you're going to have companies that are, you know, putting out lots and lots of patents, but maybe do very little R&D. And so you're still going to get this really skewed distribution in that sense. Okay. The other problem is that sort of from a theoretical standpoint, if we think about what theories of innovation are saying, they're presumably saying something about the effect of different economic factors on the number of patents, not on the patents per dollar of R&D, right? So I could imagine that the effect of doing something that sort of spurs innovation is it causes the company to just do more R&D, which leads to more patents. But if we're scaling patents by R&D, we're not going to see that, right? That may not be changing at all, even though the sort of the frequency of patents, the arrival rate of patents is in fact increasing. So when it comes to something like patent data, I think from a prescriptive standpoint, we would say you can't really estimate good rate regressions, and Poisson regressions are probably going to be the best thing that you could estimate here. Okay? Now, the reason why you might want to estimate rate regressions if you have a good exposure variable is that, generally speaking, and this is something we're still working out, so this is still very much a preliminary statement, but it appears that OLS rate regressions are going to be more efficient than Poisson regressions if you have a choice between estimating the two. Okay, and so if you want more precise estimates, OLS rate regressions may be the better option, especially in cases where you have either over or under dispersion in the arrival rate, which means that the conditional mean and conditional variance equivalent to some restriction in the Poisson model doesn't hold, which creates a lot of inefficiency in Poisson estimation. Okay. All right, so any questions? This is the last, I have a concluding slide. This is the last substantive slide I had. So I just want to be sure
there is a paper, another suggestion for a paper on fractional response or rate.
Okay.
Okay, excellent. Woodridge, and the solution he thinks is some modified logit.
Okay,
so you can have a look at that.
Yeah. Okay.
There is a question about whether if you use a continuous variable, you discretized it, and then you know, use the same methodology. Is it the same problem? Yeah.
So for what it's worth, I don't think that the discretization itself is actually a big problem, right? If we're thinking about count data, you know, the features are they can only take on, you know, non-negative integer values, so it is sort of discrete by construction. You can estimate a Poisson model with a continuous dependent variable. It doesn't have to be a discrete variable. Poisson model can estimate regressions with a continuous variable just fine. So I don't think that the discretization itself is actually important. The only place where it does become important is it means that you can't have, you know, like small fractions of numbers of patents. You're either going to have 0 or 1. And so that's going to be, you know, part of the reason why you get this kind of weird looking, kind of very skewed distribution. It's still going to be skewed even if you could have sort of fractional values of patents. But maybe it would look a little bit less skewed if you could have, you know, a third of a patent or a fourth of a patent. And that's just not something that you can have.
If you add 1 to the data in the Poisson model, does it cause a bias? Or
that's a good question. Off the top of my head, I would guess that it probably does. I don't know, Malcolm. I'm not sure if you can sort of see the econometrics any more clearly than I can. I can't give you a concrete answer to that question.
And finally, patents per dollar of R&D can be perhaps interpreted as innovation efficiency. So that might be useful.
Yeah, that's right. So you would have an interpretation there, and that interpretation would make sense. I agree. I don't think that's generally what we're after when we're estimating, estimating regressions where we're using patent data. I think that we're trying to say something about the combination of firms either sort of doing more R&D or trying to engage consciously in more patenting activity and the efficiency of that activity. I think both of those are kind of bound up in what we're trying to capture. But if all we care about is the efficiency of R&D, I agree. And then we actually probably have a pretty good rate variable that we could use, modulo the fact that you still may end up with a fairly skewed distribution. And so that's going to cause efficiency problems with the OLS estimation. But that at least potentially would make sense. And going back to the sort of Wooldridge suggestion about about estimating some type of like conditional logit model, again, that makes a lot of sense. The problem is you can't include fixed effects in that type of model. And so in the application from a practical standpoint that we're generally thinking about in corporate finance, you're still going to run into a problem where you can't include those fixed effects. And if you think the fixed effects are important, you may not want to estimate that kind of model.
That was the last comment.
All right, excellent. Okay, so I'll wrap up with my conclusions, and then we'll take questions at that point. So again, the bottom line is these log of 1+ regressions are difficult to interpret. That's one problem. I think the bigger problem is that they can be biased and inconsistent. Even if the errors in the y variable, in the count variable, are uncorrelated with x, right? Which is sorry, I shouldn't say that. Yeah, even if the errors in the y variable are uncorrelated with x, and so Poisson regressions are really going to be our sort of recommended solution here, right? You do lose some efficiency if the conditional mean, conditional variance equivalence restriction doesn't hold, but they have a natural interpretation, at least in terms of incident rates, which are sort of like elasticities, and the estimates are unbiased and consistent under the standard exogeneity assumptions. And generally speaking, that's sort of, I think, the first order criteria we would have for deciding whether or not a particular estimator is a good estimator to use or a bad estimator to use, okay? In practice, as we've seen, log of 1+ estimates frequently have different signs than Poisson regression estimates, different orders of magnitude. So it seems like from a practical standpoint, that the sort of problems with the log of 1+ regression are actually problems with real data. Okay? And again, rate regressions may be ideal, but you need a good exposure variable in order to be able to estimate those rate regressions, which I think in most applications means that the Poisson regression is probably the right form of regression to use. Okay. All right, I'll stop there. So Ryan, you mentioned there was one question that was more general.
It was the question on the continuous variable discretizing. Okay. So yeah, well, great. It looks like there are no questions at this point, but if you have questions, I'm sure Jonathan and Malcolm would love to hear them. Again, thank you, Jonathan.